So let's first start off with our assumptions. So this process is going to be fairly simple. We need assumptions, we need our hypothesis statement, calculations, and then followed by conclusions. So our assumptions start off with that we're dealing with two independent SRSs from the population, and this can be something that's stated or can be reasonably assumed from what they describe. The population is at least as big as 10 times the sample size. That it's normal for both. Now, with proportions, normally it's n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. But with two sample procedures, we actually loosen up that standard and say that the first sample's got to be greater than or equal to 5, and the second sample also has to be greater than or equal to 5, which thus is consistent for the 10. Okay, so our confidence interval for two sample proportions is the statistic plus or minus the critical value times the standard deviation. And so for two sample proportions, we end up subtracting the two p hats, and the critical value, now we're back to z stars again. And then our standard deviation is this lovely formula here where essentially it looks like we're averaging out the P1s and the P2s from the separate samples. Now, just FYI, we stick with p hat whenever the population parameter is unknown. This component we refer to as standard error. That's the standard deviation of the sample. And then when we take the z-star into account, that's what's called the margin of error. So that's that plus or minus certain percent off of the sample proportion. Okay, so let's take a look at some examples here. At a community hospital, the burn center is experimenting with new plasma compress treatment. A random sample of 316 patients with minor burns received the plasma compress treatment. Of these patients, it was found that 259 had no visible scars after the treatment. Another random sample of 419 patients with minor burns received no plasma compress treatment, and for this group it was found that 94 had no visible scars after the treatment. What is the shape and standard error of the sampling distribution of the difference in the proportions between the two groups? Okay, so whenever they're talking about shape, they're referring specifically to whether it's normal, symmetrical, bell curve, that sort of thing, or if there's some sort of skewness to it. So for two sample proportions, we're going to stick with the NP, n times 1 minus p, is both greater than or equal to 5. And so that's just going back in and sort of taking sample size times the proportion that showed up. And in all cases, it ends up being definitely greater than 5. The first sample size times the proportion of that first one would be 259, and then 57 for the other one, n times 1 minus p. And actually, let's talk a second for where we're getting this p for a second. Let me kind of get out my calculator. Okay, so let me clarify when we say probability in the first sample. So we have total, we have 316 of them. So if I'm taking 316 times, well, what percent did not have scars after the treatment? Well, that was 259 divided by the total 316. Now, if you look at that real carefully, we're multiplying and dividing by the same number, which is why we end up with 259. As far as the 57 goes, so if I do 316, which is our n, times 1 minus the 259 divided by 316, okay, that's where we get the 57 from. Kind of get the calculator out the way. Okay, so then the 94 we get from the same rationale, that it's the second sample was 419 times 94 over 419, which still gives us the 94. And then I guess it's worth showing the 325, so let me pull up the calculator again. So I guess I set it. Let me show it. Let me try that again. For the second sample, we had 419. That's that number right there. So 419 times the 94 divided by 419. And we get 94. Yay! And then the other second sample, so for the 419 times 1 minus the 94 divided by 419. That's where we get the 325. So anyways, a lot of words to basically state that we're definitely bigger than 5 on all 4 of those calculations. So we're definitely dealing with some sort of normal distribution. Okay, what about the standard error? So standard error would be standard deviation of that sample, and that was that lovely formula we saw earlier. So let me kind of, again, pull out the calculator and kind of show you how to type that in. Alright, so when we did the 259 divided by the 316, okay, that's where we got the 0.819. So then I want 1 minus that number, which is where we're getting that 0.18 from. So if I take, let's see, yeah, let me get the other percent. So the 94 divided by the 419 is the 0.22, and then 1 minus that gives us the 0.78, I guess. Okay, so to type that in the calculator, like they have it in the formula there, I want the square root of the 0.8, let's see, let me do open parentheses because I want that whole numerator to be together. So 0.82 times the 0.18, and then I'm going to close out that parentheses of the first fraction divided by the sample size of 316, plus open the parentheses of the second fraction. In the second fraction I want the 0.22, so I'm going to arrow up to that, times the 0.78, and then close off that numerator and divide it by 419. And then just hit enter. So we get a standard error of 0.0297. Now I'm a lot more accurate because I let the calculator type in all those numbers, but as long as you get something close to 0.03, then that's fine as far as standard error goes. Okay, so now we're going to sort of change the question. All the other facts are the same, but now I'm asking for a 95% confidence interval of the difference of proportion of people who had no visible scars between the compress treatment and the control group. So all of our assumptions are the same, and we've calculated most of those. There's one number we kind of need to show as to where we get this from, and that's that 7350. Remember, it's 10 times the sample size. So if I add up the two samples, the 316 and the 419, I get 735, and then multiply that by 10. So it's safe to say that the population of burn patients is at least 7,350. Okay. Then I can go ahead and calculate out the confidence interval, which would be just type in all those other numbers, the 0.82 minus the 0.22, plus or minus a 95% confidence interval would have a z-star of 1.96. So you might want to go back and look at how we calculated that from earlier. That's one of 3 numbers that I mentioned would be good to write down and sort of memorize associated with z-stars. This piece right here, the square root, we actually calculated in the last step. So let me get my calculator out and kind of show you how we could do this. Let's see, so we want 0.82 minus 0.22 is 0.6, and I'm going to do this 1.96, which is that z star for a 95% confidence interval, times that whole square root thing, but the square root thing we already calculated as 0.0297 blah blah blah. So I'm just going to add those together. Okay, so the confidence interval then would be, I'm going to add up the two values and subtract the two values. So 0.6 plus that 0.058 gives me the upper bound, and 0.6 minus that 0.058 gives me the lower bound. And so the confidence interval is somewhere between those two numbers. Now, I'm a little bit more accurate in my calculator than I am on the PowerPoint, but that's okay. I mean, the calculator, I'm being very, like, decimal digits out to 7 places, I guess. Whereas on the PowerPoint, I think I'm down to 2. But as long as we get something like that. Okay, and so then to interpret that, we would say we are 95% confident that the true difference of proportions of people who had no visible scars is somewhere between the plasma compressed treatment and the control group is somewhere between 53.7 and 65.4. Okay, let's do another problem. Suppose researchers want to estimate the difference between the proportions of people who are against the death penalty in Texas and in California. If two sample sizes are the same, what sample size is needed to be within 2% of the true difference of the 90% confidence? Okay, so 90% confidence is another one of our z-stars that we should know. So you want to take a second and go look that up. But our formula starts off looking like this, where it's 0.02 equals that z-star for 1.645, and then this is sort of a throwback to the one sample proportion. In one sample proportion, when we're estimating sample size, we would estimate the worst possible p hat, the one that had the largest standard deviation. So in that case, it would be 0.5 and 0.5. Sorry, 0.5 being the p hat, and 1 minus 0.5 is also 0.5 for the 1 minus p hat. So we go with 0.5 for both of those. And then from here we're going to do some common denominator skills. So if I multiply the 0.5s together, I get 0.25. And so I'm kind of staring at that. And then we're going to let the calculator take over and sort of work backwards as far as what that sample size should be. So I want to divide that 0.02 divided by 1.645. Okay, so now I've got that lovely that 0.012 right there. So that would equal the square root of this. So then I want to square it, and I get this decimal. So then to get n, I want to take 0.25 plus 0.25 and divide it by this number that I've now found. So 0.25 plus 0.25 is 0.5, and I'm going to divide that by that lovely decimal, and I get a sample size of 3382.5, and with sample size we always want to round up, so that rounds up to 3383. Okay.